strategic deterrence and nuclear integration. So today, excited to talk to you all about Skydweller. As was mentioned, Skydweller is headquartered here in Oklahoma City. A nugget for you as well is I retired from the Air Force and returned home to Oklahoma. I originally grew up in Noble, so if you know where that is, just south of Norman, and then came back home to Oklahoma because of some of the technologies, some of the companies that are here, and some of the opportunities that exist for technical applications and for technical oriented jobs. Oklahoma is quickly growing in the aerospace industry, and it is currently the #2 industry in Oklahoma, and is one that is going to continue to grow over the next few years as a variety of efforts are underway to expand in terms of the aerospace application and footprint here. So to kick us off here, Skydweller Aero, excited to talk to you about what we do and what we are and the processes we're going through right now from an engineering perspective, and what we're doing to bring this capability to market. Slides coming through okay, Pam?
Yeah.
Okay. I'm seeing some head nods, so good to go. So what is Skydweller? So Skydweller, what we're aiming to do is have a platform of perpetual flight. Its current platform that we're working on mostly right now is a medium altitude pseudo satellite that's capable of carrying heavier payloads for long persistent overhead applications. In terms of the aircraft itself, its wingspan has 236 feet and its weight is 5,500 pounds. So one way to think of it, it's like an F-150 with a wingspan of a 767. So really huge in terms of from a wingspan perspective. And then you can see there in terms of endurance, we're targeting 90+ days with an unlimited range that you can fly at the speeds that we can fly in that sort of time frame. But what is it based on? Skydweller's aircraft is based on the Solar Impulse 2 aircraft. I don't know if you had heard of it in the past or not, but the Solar Impulse 2 aircraft was developed to prove that you could fly with solar power. And they successfully circumnavigated the world on just solar power. It was not a continuous flight in that they took off and didn't land until they landed in the same place. They had various stops along the way because a pilot was included in the aircraft and could not stay up for the entire duration. But they proved some key aspects of the technology itself, that the aircraft was able to break that 24-hour solar cycle and actually remain in the air for longer than a 24-hour period. The longest flight was essentially for a continuous 5 days and nights. It was a little shy of a total 5-day, 5-night cycle, but pretty close, and proved the idea that you could have an aircraft with perpetual endurance. Another key aspect of this aircraft is it was actually certified to fly over densely populated areas because of where it had to transit. They got approvals from in both Europe and the United States to be able to fly the aircraft itself over densely populated areas. You can see here in terms of, gives you a little perspective of the aircraft. You can see some people on the ramp there. You can see the comparison between the size of the individuals and the size of the aircraft. You can see across the entire top of the wings, those are all solar cells across the top of it. You might be able to see down the body of the aircraft as well as in the tail. Again, solar cells cover pretty much every vertical surface or every horizontal surface, excuse me, on the aircraft in order to gather enough energy. Across the top, you can see the longest flights that the aircraft took. The almost 5-day flight was from Japan to Hawaii, and that was in June of 2015. From there, from Hawaii to San Francisco in a little over a 2-day flight, and then another long one going across the Atlantic. You can see there later in June of 2016. So you might notice a long pause there from 2015 when it landed in Hawaii to 2016. They had some challenges with the advanced batteries on the aircraft itself and had to replace some of the batteries. So that was kind of a pause there. Again, the idea that an individual flew around the world continuously, that didn't happen in this case, but they did circumnavigate the world on nothing but solar power. So what is Skydweller doing with this aircraft? Well, let me pause for a minute. So in comparison, you may have heard of some other solar aircrafts that are out there and want to give you an idea in terms of how does Skydweller compare to these other aircraft. You can see here in terms of a variety of them, an Airbus Zephyr, a BAA Fascia 35. You may or may not have known that Facebook tried to make a solar aircraft in the Aquila. Google tried it with the Solera 50. Boeing had the Odysseus, and then SoftBank has the Sunglider. If you'll notice of the Facebook Aquila and the Google Solera and the Boeing Odysseus, each of these planes have actually stopped. They've canceled those programs for now. You can see the SoftBank Sunglider is stalled as well. It's a very challenging thing to be able to develop a solar aircraft that can fly and can fly perpetually. You can see Zephyr and Fascia 35. One key thing here is to compare in terms of the aircraft weight relative to the Skydweller. Skydweller is the largest solar aircraft out there, if you will, at 5,500 pounds and 236-foot wingspan. You can see for the Zephyr, it's only 165 pounds and 73-foot wingspan. The Zephyr and the Fascia 35 are focused on flying up in the stratosphere, whereas the Skydweller aircraft is focused on flying in medium altitudes. Another key difference in our aircraft is it was developed around being able to carry an individual, right? And so there were different requirements from a aircraft structural perspective and safety perspective when you think about what's required to make sure that individual stays safe. Because of that, we have a much more robust structure and ability to fly in medium altitudes. There have been a lot of challenges with these solar aircraft. The Zephyr has had a couple of instances where the aircraft broke up in flight when it was transiting from the medium altitudes to the high altitudes. Whereas with the Skydweller aircraft, yes, we're sensitive to weather conditions and a variety of factors, but we're far more robust when you consider our structure. One other key aspect I'll point out here is if you look at payload weight and payload power. The Skydweller aircraft, we would estimate a payload power availability of 2,000 watts, and from a weight perspective of 300 to 800 pounds. Where are we gaining all this payload capacity? A big aspect of that is, again, the aircraft was designed to carry a person. Now, if I remove the individual, calculate the weight there, I remove the chair, the safety functions, the human controls, the human interfaces, and all those aspects, it gives us a lot of room for more payload potential than some of these other systems, which are much, much smaller. So it is a very unique capability in terms of how it was designed under the Solar Impulse Foundation. And what we're doing is converting it into an unmanned variant, removing all those systems and capabilities that were required for a human in the loop on the aircraft itself. And that gives us a lot more opportunity in terms of payload weight and what we can actually do with the aircraft itself. So what applications are we targeting? Two main areas that we're looking at is from a government surveillance perspective and supporting long-term intelligence, surveillance, and reconnaissance missions is a key aspect. But more importantly, I think to a degree, I think we might see greater growth, is looking at broadband communications. The ability to have a system that can go up in an area and establish either cellular coverage or broadband communication coverage is kind of where we think a key niche area for us is. You may be familiar with low Earth orbit satellites providing some of those sorts of services, and you may be familiar with satellite towers providing some of those services. There are challenges and benefits of each of those technologies, and we think that the Skydweller capability fits between those two areas and provides us an avenue for increasing communication reach to areas where individuals don't have that connectivity, or areas where there's trouble having increasing coverage in an area to a 4G or a 5G technology as opposed to a 2 or a 3G coverage. Talking about that just a little bit more, what you can see here is two potential ideas, if you will, from a coverage perspective, and what sort of sight picture you have on the ground from a Skydweller type aircraft. Our altitude operating ranges are in that 10,000 to 40,000 feet, and that obviously affects your spot size on the ground. But you can see that you still have a fairly large coverage perspective using either broad area coverage at 100 kilometer diameter there, or a focused area coverage in 20 kilometers. So it could allow you to reach areas where you don't want to have a long and expensive development project in terms of building in the infrastructure necessary from a terrestrial basis. It also allows you to have coverage where you don't have necessarily fast revisit times from a low Earth or orbit satellite. Another potential application is if you have a disaster response or emergency type perspective, and you need to bring in some temporary coverage, if you will, the Skydweller aircraft could potentially have a capability that would allow you to increase coverage in an area in response to a hurricane, tornadoes, or other life-threatening events, if you will, that damage a lot of the infrastructure in place already. Another idea on this too is in terms of gap fillers in coverages. Skydweller has the potential to fill numerous smaller gaps, and then also replacing the potential of towers with existing 5G, 4G coverage areas for cellular sort of coverage. We've all driven in places where our cell phones have dropped out, if you will, and that has to do with angles between the cell tower and yourself and a variety of other things. Now, as opposed to if you are higher up where the Skydweller aircraft is, your ability for that signal to actually reach the customer on the ground is increased, and your likelihood of dropping, if you will, is far less likely than it would be if you're reliant solely upon the cell towers themselves. So you can see in this picture where in number one, the customer is connected to the terrestrial tower whenever that signal is available. As they transit into areas where the signal is blocked, now it potentially switches to a signal from the Skydweller, and then from there, potential to switch back to the terrestrial towers, if you will, as it rolls out of those blocked coverage areas. So you can see here in terms of a variety of applications where Skydweller could be a key technology expander, if you will, for communications coverage globally. Now, it's all based on key aspects of technologies. And there's a variety of research areas that we at Skydweller pursue. And to just kind of give you first an overview of some of the research areas, but then I'll talk to three key areas that we are very deeply working on right now, or very interested in, if you will. So multidisciplinary design optimization. As you can imagine, an aircraft like Skydweller, every aspect of the aircraft is coupled. If weight increases, that affects energy usage. If solar coverage isn't what it should be, that affects in terms of energy production. If you have increased drag, that again increases, that affects the energy that you need to fly the aircraft. So all the aspects of the aircraft are tightly coupled in terms of, in order to have a design solution that works and enables you to hit that perpetual flight basis, you have to consider all the factors in an aircraft. For powered flight, as your typical jets out there, you can typically compensate by saying, let's increase thrust, let's add a little more fuel, let's do some of these things. In this case, if I say, let's make a bigger battery, well, the bigger battery is more weight. The more weight means it takes more energy. Do I have enough energy production in the solar cells on top? If I do, that might be okay, but then do I have enough storage capability? And it's very easy for an aircraft like this to what they call unwrap in terms of its ability to actually meet the mission profile that it needs. And so that's a key aspect for us, is considering as we look at our current aircraft and optimizing it for unmanned flight, but also as we look to variants that might be more optimized for stratospheric flight, we have to take multidisciplinary design critically into account. Next to that, you can see structural optimization. What was done to make the Skydweller aircraft itself in the Solar Impulse 2 and the structures associated with that were pretty incredible. You can see there in terms of, that's called the wing spar in that picture, which is one of the key elements across the aircraft. Because our wingspan is so large, you get a lot of flexion in the wings themselves. And so being able to make sure that can flex enough without causing problems, but not too much, is a key aspect of designing the structure such that it takes those aspects into account. And so structural optimization and coming up with new tooling, new materials, and taking what was done in the Solar Impulse 2 and integrating more aerospace applications, aerospace technologies into it is a key aspect of that structural optimization. I'm going to move down below multidisciplinary design and touch on active load alleviation just briefly as well. As you experience gust fronts and different things, if you just have standard new flight, you have to design your structure such that it can withstand any sort of any sort of wind or any sort of gust fronts with factors of safety involved. But if you can integrate a control system that can respond actively to what the aircraft might experience, that potentially reduces what you have to do from a structural perspective as well, allows you potentially to trim more weight off the aircraft and increases your capability. So another key area for us is exploring that. I'm going to shift now to the top towards power systems. High energy, high efficiency batteries is a key piece for us, as you can imagine. Everyone's fairly familiar with lithium ion, but what's next? And that's what we're looking at Skydweller, and I'll touch on that more in a minute. High efficiency solar cells is a critical piece for us in that the Solar Impulse 2 aircraft was around 22-23% efficient solar cells. Where are we going to get additional gains? Again, I'll touch on that more in a little bit, but also looking at other alternative power sources, whether that's a hydrogen fuel cell and hydrogen storage on the aircraft, or other hybrid power architecture that allows us to incorporate both solar and hydrogen and whatever else might come around that we want to look at. On the bottom, a key thing for us, as you can imagine, is weather. I won't touch on that a lot here because the next slide dives into that. But lastly, on the bottom right is UAS development itself. The controls that's needed, the flight path optimization, the considering in terms of the weather and integration weather considerations into flight, all those are critical aspects of what we're looking at and doing here at Skydweller. So to dive into a couple of slides, just to give you a little more information on a couple technical areas. So one, as a solar aircraft, all solar aircraft are very sensitive to weather, and improved weather forecasting is a critical aspect for us. So on the top left, obviously clouds would be a problem for solar energy production. If you make it to the stratosphere, that's less of a concern, obviously, because you're flying above the cloud deck itself. But operating in a medium altitude, Skydweller is definitely concerned with and aware of and trying to better predict in terms of cloud formation. You see here in the turbulence and aeroelasticity picture, a picture of the NASA Helios aircraft. It wasn't on my initial list, but it also was a solar powered aircraft. This is a picture of it actually breaking up in flight in a flight it took out of Hawaii. Again, it experienced an unexpected gust front, which caused a moment across the aircraft that caused further vibrations, and then it just shook itself apart, if you will, until it broke up in flight and splashed down in the ocean. I would say the Skydweller aircraft is more robust than the NASA Helios, but it's still something we have to be cognizant of and aware of and planning for in terms of our engineering from a structural perspective, but also, as I touched on before, from can we develop an active response system, active control system to alleviate gust fronts. But broadly speaking, in terms of, there are three, we look at weather in a tiered structure, if you will. One being the climatological understanding first of where is it even feasible to operate? If you know in northern latitudes in the winter, solar availability is very low. And so that isn't necessarily an area you're going to be able to fly year round. So understanding from a solar perspective, understanding from a weather event perspective, hurricanes, normal storm seasons, all those aspects are key factors that affect in terms of where do you think you can operate. So you can see here in the bottom left, perpetual flight 3 to 9 months more potentially in the northern latitudes, the sweet spot, if you will, around the equator from a solar availability, as well as some favorable winds. And then again, in the southern latitudes, perpetual flight in that 3 to 9 month range as well. So first tier that we look at from weather is climatological understanding of where can we operate. Second tier is in the top there is that long range forecasting. Single model forecasting solutions are not robust enough to predict weather for longer durations. We all know the weatherman, if he's right about 30% of the time, he's doing pretty well. But for our aspects of looking further out, we need more robust solutions that enable us to have a little more confidence in terms of mission success for a flight. So we are working on an approach where we look at super ensembles and prediction methods using a much greater amount of forecasting capabilities that allows us then to look at from a confidence perspective of if we were to fly a flight profile through what's forecasted in all these different ensembles, what is our confidence that we can have a successful mission? And also understanding what is the variance across these different forecasts. All right, is it so wide that it's indeterminate in terms of the solution set that you're looking at? Or is there enough agreement across the ensembles that you can have a little more confidence, one, in the weather, but two, in what probability of mission success is? And so this longer range forecasting is more from a mission planning profile and perspective. And then finally, in the bottom right is in-flight analysis, understanding in finer space timescales, what is the weather hazards I'm potentially to face? What are the wind directions that I'm looking at in order to allow you to optimize flight paths and mission profiles for station keeping, if you will, for responding to what may be coming your way, or for saying clouds are coming in this area, I need to move X, Y, or Z. Our aircraft flies really slow, so you have to be very cognizant of these finer scale analysis at long enough times that you can actually potentially respond by moving the aircraft if critical, or understanding what you might face and how you might position the aircraft for what may be coming your direction from a weather perspective. So you can see here a tiered approach, if you will, in looking at weather and when considering operations of a solar powered aircraft. The next aspect that is critical for us is improving our power generation capabilities and our power storage capabilities and energy storage. So on the top left is a plot of where solar cells have gone. And this is a plot produced by NREL, a DOE lab in Colorado, that looks at advances in solar cell technologies and where are we at in terms of solar cell efficiencies. There are some theoretical limits that we are approaching from a silicon solar cell basis. So Skydweller is actively looking at what other options out there. As you can see in the bottom left, we have 190 square meters of solar cells on the aircraft itself. So we are very interested from a solar perspective of increasing the efficiency of those solar cells. We aren't going to add any more horizontal surface area on the aircraft itself. So we need solar cells with improved efficiencies, but we're also looking at, are there other solution sets out there that we can integrate, whether it's passive absorption for albedo effects on the sides or undersides of the wings, but where can we squeeze out more energy production in the aircraft that we could potentially use? As I mentioned earlier, in terms of where we're at in terms of solar cell efficiency, we're in that 22-ish% range. Ideally, we'd like to hit 30 or above 30%. And there's some interesting technologies out there, whether it's perovskite solar cells. Gallium arsenide is more of a space application, but it has potential. The challenge with it is it's very expensive from that perspective. It would be a factor of 10 at least more for Skydweller to integrate a gallium arsenide solar cell versus current silicon solar cells that are out there today. Again, and then lastly on the right here is looking at advanced battery technologies. We talked about before that, state of the art, if you will, is lithium ion to a degree. When the Skydweller, when the Solar Impulse 2 aircraft flew, it had a lithium polymer battery at that time, which was key state of the art, but that was 7 years old. Transitioning to a lithium ion now might be a decent solution in the interim. That's comparable in terms of energy density to what was on the Solar Impulse. As you can see down below, looking at gravimetric energy density is key to us. Volumetric energy density is important too, but the gravimetric is more because weight matters more in the aircraft. You can see there from a lithium ion battery solution set, you're around that 200 watt hours per kilogram. Whereas we're wanting to get to more the 450 to 500 watt hours per kilogram. And so one potential solution is looking at lithium sulfur batteries. And it's one we're investigating today to try to get us above 400 watt hours per kilogram. But understanding those technologies is really important as well. A challenge with lithium sulfur is as the battery goes through its cycling, it swells and it contracts. And so understanding what might be needed from a compression perspective is a key aspect for implementing that technology on our aircraft. And if it takes more weight, if you will, to be able to compress the cells, it's going to cause more challenges and it's going to decrease in terms of what you might gain from a gravimetric energy density over what you might have on paper, if you will, from a single cell sitting on its own. So understanding all those aspects of the technology is important as we look at integrating new technologies into the aircraft. I think we'll always be an early adopter of new battery technologies with higher energy densities, but it's also important for us to understand what is required to make those work. So overall, the Skydweller aircraft itself has essentially a zero carbon footprint. You know, our power sources are the sun and potentially hydrogen. If we integrate a fuel cell onto the aircraft, and it enables us to have a persistent UAS capability day and night with a carbon neutral aspect. So a breakthrough capability that allows us to do our part, if you will, for a cleaner environment. My kind of get off the stage here is to show you all a video of the aircraft in one of our flight tests. Hopefully everything on this comes through just fine. We tested a little bit ago, but this should give you an idea of the Skydweller aircraft in flight. And with that, I'm happy to take any questions you might have about Skydweller and about some of the technologies that we're looking at. I appreciate your time today, and it was great to be able to talk to you.
Thank you, Dr. Amendt. If you can stop sharing on your screen, then I think we can see the students who might be raising hands or come on with the questions.
Looking in the chat, how about I start there and see what we can go through here. So question here, are there pilots in the planes? Currently, yes. We currently do have a test pilot in the aircraft. And what that does for us right now as we're converting from a manned version to unmanned is it enables us from a flight perspective to use some of our past approvals for flight and maintain our test program. Now we are headed towards this year is our goal to hit our first autonomous flight. And so once we start that, we will transition from a manned aircraft to an unmanned aircraft. Any other power in this plane? Touched on that a little bit. Predominantly solar power is the main aspect that powers the aircraft, but also looking at the potential to integrate a hydrogen fuel cell as an alternative source of power. S here, will your aircraft be governed by military GPS to move your system from place to place? We will likely take advantage of GPS, at least as a potential navigation tool, but I don't know what's essentially meant in their question there for governed by military GPS. We can use commercial grade GPS that's out there as well. And so we have the potential, at least for our commercial applications, to go that route with it. Interesting question here. Lithium is an element mainly held by our adversaries. What is available moving forward? Yeah, lithium China is one of the largest producers of lithium out there. And that's always something that we try to take into account and consideration in terms of who is providing the materials that we're integrating into the aircraft. I think that's something that everyone should, commercial or non, take into consideration of where is your raw materials coming for and understanding from a market perspective of the dynamics that can affect that. Is there a lot of alternatives there? I'm not aware of a ton of alternatives from a lithium perspective, but one key thing that we have been watching is as well as the ability to recycle batteries and what is the potential there. And that's a key factor too. You may see some information on lithium sulfur batteries, and the ability to recycle lithium sulfur batteries is a little bit better than some of just the lithium ions. So those are all key aspects that you want to understand. I guess I'll take a couple hand questions for now. Is it Rohit? Is that how you say that? I'm sorry.
Yes, Rohit Nair, OKC. How fast do you expect the Skydweller to go, typically with like a full cargo load?
It's a very slow aircraft. So in that 20 to 40 knot category is typically what we talk about from a flight speed perspective. Looks like Suresh has his hand raised.
Yeah, Suresh Pasula, Edmund. So is Skydweller ever going to step into commercial passenger flight with solar power airplanes?
I would say that would be a big stretch for us right now from a weight capacity perspective. If you understand in terms of the aircraft right now and its ability to have a person in it. So if you think about the manned version of all those aspects, pretty much tapped out the aircraft from a weight perspective, and that was to have one person in it. If we were to talk about or think about trying to have some sort of passenger transport capability, I don't think that would be feasible using just the solar power aspects. There are some interesting research projects and programs out there, if you will, looking at NASA is putting together some competitive design aspects of looking at hybrid strategies, using hydrogen power as one. And so it'll be interesting to see where they go with some of those advances. But from a solar generation perspective, unless we get a lot more efficient solar cells and the power generation increases such that it can overcome the weight limitations, I don't see that as a future path for Skydweller right now.
Thank you.
Yep. A couple more questions came in the chat. Is there a projected yearly maintenance cost? If so, how does it compare to the yearly maintenance costs of the infrastructure it would replace? That is actually one of the key arguments from a military surveillance aircraft perspective, is Skydweller is really cheap relative to operate relative to your traditional aviation fueled aircraft. Part of that is the fuel costs themselves. If we look at what we would potentially do, we have about a 90-day window is what we are currently trying to hit in terms of time to remain in flight. And a lot of that has to do with reliability of aircraft parts and the need to check those over time. What might potentially, it depends on the life cycle of the batteries themselves. Right now, we're looking at, can you trade cycle capability of a battery for more power, such that you might have to replace the battery more often, but you have greater capability. So it is a potential possibility of switching out a ship set, if you will, of batteries on the aircraft, that has to happen based on cycle lifetimes. But we're also looking at higher cycle life batteries too, that would last for 5 to 10 years. So it just really kind of depends on what is needed or desired from a capability perspective. Higher performance will probably have a higher cost in terms of logistics. Higher or lower performance, but higher cycle life would have less of a cost from a logistics perspective. And so from that, but overall, even in both of those cases, it is cheaper than flying a jet fuel powered aircraft. Question here. As you will be coming to Ardmore eventually, is the plan to build planes here or only for test flights? It's kind of to be determined a little bit right now. We recently signed a lease with Ardmore for a space at the airport, excuse me. Kind of current vision of that is it'll be a good location for us to potentially integrate any sensitive payloads, if you will, that need to be integrated from in a US territory. Skydweller is an international company in that we have our headquarters here in Oklahoma City, and we have a Spanish subsidiary near Madrid, Spain. Currently, the aircraft is in Spain because it was in Europe already, and then COVID hit, and it just made sense to keep it there for now. And we haven't figured out for sure in terms of where exactly the production of, let's say, the structure will be and the integration of that, and then the transition to a location where you potentially could integrate other more sensitive payloads that Skydweller itself might not make, but would have to be involved with the integration aspects of it. So to be determined what exactly will occur in Ardmore, but we're excited about the opportunities that we have there, and excited to get our lease signed just recently. Question here on cost. Oh, no, weight, excuse me. How much the aircraft currently weighs. It's around 5,500 pounds. So again, the analogy of an F-150 with a 767 wingspan. Does Skydweller have internships? Absolutely, we have internships. We predominantly do internships right now at the collegiate level, but we're exploring opportunities for how we could bring in high school students and make a interesting and useful experience for high school level students as well. Does the company only focus on integrating fuel battery cells on aircraft, or do they also learn how to store hydrogen for efficient use in cells? What are we doing to improve storage of hydrogen in fuel cells? So hydrogen isn't stored in fuel cells themselves. It's usually an external storage of hydrogen. There are three options for that. One is gaseous hydrogen, one would be liquid, and one would be a solid state in some sort of cartridge or cartridge is usually where you see it the most. We are working with some other Oklahoma companies. Infinite Composites is one, to try to see if we can improve the hydrogen storage capability of one of their tanks of interest to us. Liquid storage would be really interesting as well, but there are a whole host of challenges with liquid storage, and it's quite a bit more expensive. But there could potentially be a breakthrough from a liquid storage perspective, and that would be very interesting from an energy density of the hydrogen stored, and that would be of interest to us as well. What is its range? Can it fly here from Europe, or would it have to be shipped? The Solar Impulse 2 aircraft definitely flew from the United States to Europe. So is it possible to fly across the ocean? Absolutely, it's possible. If you are producing aircraft in Europe and you're trying to transit them somewhere, you would most likely ship it, I would think, rather than just flying it. But to be determined from that perspective. How much did the whole project cost? Tough to give you a solid number on that. I can say this: the Solar Impulse 2 Foundation spent over $190 million in developing their aircraft. They developed it over a 10-year time span, and they actually developed 3 different airframes, 2 prior to the Solar Impulse 2. And so Skydweller has built the company, if you will, on that technological basis of what was developed in the Solar Impulse 2. We've invested quite a bit ourselves in advancing it to where we are and to get us to an unmanned state this year. So it's definitely not cheap to develop a solar aircraft, and it takes a lot of patience in order to go through that process. Any other questions out there?
Yeah. Can you mentioned thin film earlier. Can you talk a bit about, is there anything you can share about some of the high-tech materials used?
So in the structure itself, much of the structure of the Skydweller aircraft is a carbon fiber material that requires specific layups, if you will, in terms of gluing, for lack of a really better term there, of gluing the layers of carbon fiber together in order to make the structural components. In terms of the solar panels, so each solar panel, you might have caught it in one of the pictures, each solar panel is about 9 feet long. Now that's integrated with a variety of, there's numerous solar cells themselves in the panel. So the way we produce those is we take the solar cells, you essentially weld them together. So in the strings is what is the term that's used to hit a voltage of interest. And then you put those strings in orientation in the panel, and then you press the panel together, that then it can be integrated on the aircraft. It's a fairly labor intensive process right now. So the solar cells themselves are pretty state of the art, using a variety of materials to encapsulate them in order to make a panel itself. But then the carbon fiber is another key technology for us that's integrated throughout. What's interesting, I touched on it briefly in terms of the spar of the aircraft, that long beam, if you will, that goes inside the wing. That was actually when the Solar Impulse Foundation came up with that spar, they were using some advanced sailing materials to make that. And so we think there's a good avenue there for us to trim some weight by integrating aerospace materials as opposed to kind of your America's Cup sort of sailing materials in that.
All right, I think that's about all the time we have. So thank you, Mr. Amendt, for speaking with us today. And I do hope you're able to come visit us soon when the weather and pandemic permits. Thank you, students, for your patience as we tried to get everyone in here today. I know not everyone was able to join, but we will send out this recording to everyone else. I just have a couple of minor things before I let everyone go. So after this, everyone will kind of go along with their normal Wednesday afternoon schedule, like we normally have when we have assemblies. And so if you're over in the residence hall, then you'll have to come on over to here. Now, there is weather coming in. I think it's coming in just probably any minute now. So as you're on campus, just kind of watch your step, especially on the sidewalks. Our Mr. Madden and Mr. Forsey should be out putting salt on the sidewalks, but nevertheless, just watch where you're walking. And again, of course, if your classes, if your teachers are off campus and they're not able to get in either today or tomorrow, then they'll notify you and either hold class virtually or give you stuff to work on. But we are planning to have, as best we can, our normal schedule. And unless anyone else has any announcements or questions, I think we are done.
Oh, this is Dr. Wong. Just want to say that we will be meeting in person in our usual classroom 5. So just want to let the students know. So thanks.
It's just Dr. Wong's class. That's not everybody. All right. Well, thanks again, everyone. And hopefully we will see you tomorrow.
Dr. Amendt, thank you again very, very much. Fascinating and lots of great questions. That's fun for us to hear too.
My pleasure, Pam. Glad I could.
Yeah, thank you so much. I appreciate it. You don't see me because I don't have a camera on my computer. So
Sure.
Dr. Amendt, Warren Thomas is one of our foundation trustees. You met Brezzy earlier. And Ron Mashore, he's got his camera off. He's muted down there, I think.
Gotcha. Nice to meet you all.
Okay, well, we'll have a link if anyone would like to have the link to watch this. Students, do any of the rest of you, do you have more questions you'd like to ask? I don't know if you have the time, Dr. Amendt.
I've got a couple more minutes, but if there are some.
Oh, it turns out I do have a camera. Dr. Richards just came in and pushed something on my screen. So thank you for a great presentation.
You're welcome. Glad I could do it.
Sydney, Natalie, do you all have a question? Would you like to ask anything? Okay, glad you're here. Apparently not everyone was able to get in, which I'm surprised about. Sorry to say, but we'll provide the link for them.
Well, thank you very much. I appreciate it and look forward to visiting sometime and being able to meet you in person. So
great. Thanks again very much.
Yep.
Appreciate it.
Everyone stay safe.
Yep. Thanks.
Bye.
Bye-bye.
Bye-bye, everyone.